All right, let's get into it. Today we're going all the way to the top floor of the internet, the penthouse suite, you could say. We're talking about the application layer, the part you actually see and use every single day.
I mean, ever really stop and think about that? You've got your browser, your email, Spotify, maybe a game running. All of them are sharing the exact same internet connection. So how on earth do they manage to talk to the right places without getting all their wires crossed? Well, the answer is all in the application layer.
So here's what we're going to cover. First, we'll see why this layer is basically the whole point of the internet. Then we'll look at the two main ways apps are designed to connect. After that, we'll dive into the rules of communication they follow, explore the huge trade-off between going fast versus being reliable, and finally, we'll see how this whole setup created an amazing platform for invention.
Okay, first up, where the internet really begins. Now, I know there are tons of complicated layers underneath with routers and cables and all that stuff, but this layer right here, this is the reason for all of it. It's the whole point. This is the layer that you and I actually interact with. It's home to your web browser, your messaging apps, your online games, everything. And what's really cool is that the rules for communication up here, the protocols, are often written in a way that's almost human-readable. That makes it the perfect place for us to start to really understand how this whole thing works.
So when someone builds a new app, how do they actually design it to work on the network? Well, it turns out they generally start with one of two basic blueprints, two fundamental models for how all the different pieces are going to talk to each other.
The first one is the classic, the one you're probably most familiar with, the client-server model. Think of it just like a restaurant. You've got one central kitchen, that's the server, it's always on and it has a permanent address. Then you have all the diners, those are the clients, who show up whenever they want. The diners talk to the kitchen, but they don't really talk to each other. Web browsing works exactly like this. Now the other model is peer-to-peer, or P2P. Here, there's no central kitchen. It's more like a potluck dinner. Everybody brings a dish and serves everybody else. Each peer is both a client and a server, talking directly to one another. This is really common in things like file sharing systems.
Okay, so we have these apps, and they're either clients and servers, or they're a bunch of peers. But how does a message from your laptop manage to find the exact right application running on a server maybe halfway across the planet? To do that, it needs a very, very precise address.
It all starts with something called a socket. And honestly, the best way to picture a socket is to just think of it as a door. Your app writes a message, shoves it through its own private door, and then trusts the internet to get it to the right door on the other side. Simple as that. Every single connection has two sockets, one on each end of the conversation.
So how does the network know which door to deliver the mail to? It uses a two-part address, just like the Postal Service. First, you have the IP address. Think of that as the street address for a big apartment building. It gets the message to the right computer. But once it's at the building, it needs to find the right apartment, right? That's the port number. It tells the computer which specific application should get the message. This is how your computer knows to send an email to your email app and not to your web browser. And many of these apartment numbers or ports are standardized. They're well known. For example, web servers almost always live at port 80. Email servers usually hang out at port 25. These common agreements are what let your browser connect to literally any website in the world without you having to lift a finger.
Okay, so the message has arrived at the right apartment. But how do the two apps inside actually understand each other? They use a protocol. And a protocol is just a fancy word for a rulebook. It's the shared language that defines exactly how the messages should be formatted, what order they should be sent in, and what to do when you receive one.
So our apps have an address, and they have a language. But when they send those messages out the socket door, they're handing them off to the layer below, the transport layer, to actually get them delivered. And that layer offers a really fundamental choice.
You know, because not all apps are the same. Think about it. When you're sending an email, you absolutely cannot lose a single character. It has to be 100% perfect. But what about a video stream or an online game? Losing one tiny little packet of data here or there is totally fine. You'd never even notice, as long as the action keeps moving fast. They have completely different needs.
And brilliantly, the internet provides two main services to handle this. On one side, you have TCP, the reliable one. It's a perfectionist. It guarantees every single piece of data arrives, in order, no exceptions. That's what your web browser and email client use. On the other side, you've got UDP, the fast one. It's all about speed. It makes a best effort to deliver the data, but no promises. It's perfect for things like video streaming and gaming, where a little bit of loss is okay, but lag is the enemy. The key is, the app developer gets to pick the right tool for their specific job.
All right, now let's zoom all the way out. We've seen the building blocks, the architectures, the addressing, the protocols, but the real genius, the truly incredible thing, is how all of these pieces fit together to create a stable platform that just unleashed unbelievable innovation.
Let's go all the way back to 1971. A programmer named Ray Tomlinson invents networked email, and he has this problem. He needs to separate the user's name from the computer's name, so he looks down at his keyboard and he picks the @ symbol for one simple reason. It was pretty much the only character that wasn't already being used for something else, a decision made out of pure convenience that is now a part of billions of people's daily lives. It's wild. This quote from Vint Cerf, one of the fathers of the internet, just hits the nail on the head. Because of this layered design, an app developer doesn't need to know anything about fiber optic cables or Wi-Fi signals. All they need to know is how to open a socket and speak a protocol. This isolation of knowledge means anyone with a good idea can build something amazing.
And boy, did they invent things. Think about it. This stable platform, designed back in the 70s, was what made the World Wide Web possible in the 90s, and that very same architecture was what the smartphone revolution was built on in the 2000s, leading to this explosion of mobile apps. Each of these world-changing innovations was built on a foundation designed decades before anyone could have even imagined them.
So here's the big takeaway. The internet wasn't designed for one specific purpose. It was designed to be a general-purpose platform for invention. That simple but incredibly profound decision allowed it to support things its creators never, ever dreamed of. Which, of course, leaves us with one final, exciting question. What's going to be built on this platform next?